begin. Welcome to another episode of the Common Lisp Study Group. I'm your host, Ron Bate. I'm with Atlanta Functional Programming. Last week, we started talking about building software tools in Common Lisp, a chapter in PAIP that discusses how to refactor some pieces of our code that we wrote for the different programs that we covered, General Problem Solver and ELIZA, into some general purpose routines for the purposes of effectively code reuse and use in other different contexts. We ended our discussion last week with the actual creation of a small tool for not pattern matching. We talked about the pattern matching, but the REPL, where you ended up using what's called the interactive interpreter pattern in Common Lisp. And it was a pretty simple pattern, if you recall, that basically leveraged what is already available to you in Common Lisp for creating essentially a read eval print loop. And if you recall that the basis of all Lisp interpreters, in fact, is effectively loop, okay, print, eval, read in that order. And what I mentioned was last time is if one were to create different um, readers, as long as they converted their reader from, say, uh, the non-Lisp syntax that they use, or whatever natural language syntax that we use, where in the case that we were talking about, it was the um, ELIZA that was taking in natural language and actual uh, uh, um, specifically English, and it was able to actually convert it into S expressions. We can actually convert it using read tables or other matters to actually go in and convert it into S expressions, and then leverage this same sort of pattern to actually go and run a interpreter to do dialog commands. So you no longer have to write all this boilerplate anymore. You just really need to focus on read to write essentially what's called a lexical scanner for your particular language, and in many cases a semantic parser, because of the fact that if it's natural language, you want to make sure that structurally it fits a particular sentence structure before converting it into, say, S expressions, and have that get thrown into your interpreter for purposes of actual evaluation. Today, we're going to be talking about another aspect of generalization, one specifically for um, uh, rule-based translation, and that is something that we want to focus on, mainly because for those who are looking at Chapter 6 also talks about these the generalization for pattern matching, but honestly, the pattern matching stuff I think is pretty straightforward in terms of how it gets generalized. That I didn't want to really touch base on that particular piece, at least for me. If folks are interested in us expanding on that a little bit more, please feel free to put um, some comments in our video. And before I continue, obviously, if you like our content, please subscribe or hit the bell icon for new content. And hopefully, new content and new suggestions would get scheduled accordingly. Um, to begin our discussion on the rule-based translation, I need to first do some setup. Once again, I have to first load in our workshop here, which I forgot to prior to our discussion. AFP, PAIP, workshop. And let's go ahead and clear that REPL so I don't have all the output being there. And let's go ahead and also, for completeness sake, open up PAIP's Lisp discussion, particularly the auxiliary function um, program. We 1 second for some reason. Oh, right. Let me open up this one thing. Okay, let me try that. Okay, let's see, PIP Lisp. Okay, so Lisp, and let's bring up the auxiliary function stuff. Actually, no, let's pull up the Eliza.lisp, which is what we really want to do. And for those who've been looking at the Eliza, that PM stuff, we're going to be touching base later on when we discuss some other topics. So, um, all right. Last time when we talked about Eliza, we used this thing called Eliza rules as a function to actually grab our input that we printed out in our reval parent loop, which we didn't actually in this case uh, refactor this particular code to leverage the interpreter pattern that we created last week. Um, but we kind of want to know what this function actually does, all right? This is coming from actually the Eliza 1 function class, which basically does something like this. It is a predicate rule that goes and does a search across a set of rules in a rules database, and it checks to see if the pattern matching of that input, okay, which we would consider to be like maybe the if input, matches the actual rule that we're actually encountering, which we, in this case, if you recall, the rule was actually a structure that taked in a rule pattern, a rule result, and the rule pattern is essentially taking the first of the cons pair that this rule is structured and returns it as part of the rule pattern. And the rule result comes in, or the option of the rule result comes in when you do the rest. And in this particular case, we check to see if this matches and if the result is not equal to this generic fail function that the constant that Norvig created. It'll go ahead and then uh, populate the response with the switch viewpoints function that we use to change the sentence structure so that it looks like a response rather than a canned structure or sentence with the variables. Um, One thing that I wanted to bring up about this is according to, and this is kind of what the book was kind of alluding to when I read this, is this notion of searching through rules is pretty typical in not just these kind of question answer response systems, but in other systems in general when we're talking about classical AI systems. If you recall, for those of you who have probably studied a artificial intelligence course, a lot of the basic classical AI problems tend to be revolved around this notion of search. And we're going to actually cover not just this rule-based translation search issue, but also something similar, leveraging trees later on. We may not cover, for those who are hardcore into AI, the standard algorithms in search. I may end up creating a separate video on this. And by standard algorithms for search in AI, we're talking about things like A star, alpha beta pruning, and things like this. That's actually going to be a much more involved discussion. I'm mainly focusing on what was covered in the chapter. So those who are interested in that, this is probably going to be a follow-up to this particular discussion, mainly because of the fact that, at least from my reading of 6.3 and 6.4, the focus is more on basic searches like breadth first and depth first search, which we will cover here. Um, we may not cover some of the pruning algorithms that are typically associated with search. At least based on what I read so far on chapter 6, inside chapter 6. And those of you who came in about talking about the who are thinking that we may be covering also a little bit of chapter 7, I'm sorry to burst your bubble. Unfortunately, this turned out to be a much bigger chapter than I originally thought it was. So we're only going to be covering really 6.3 and 6.4 today, and we may not even cover all of 6.4 just because there's a lot of notions on graph searches that I want to kind of spend some time on just to go in depth into some of this stuff. So given this this use ELIZA rules function, um, let's try and see if we could generalize this into kind of a set of tool, kind of a function that could be used in uh, a generic way. Okay, the first thing we need to ask is a couple of questions, right? Um, what kind of rules do we want? All right. Uh, And this is kind of what Norvin kind of pointed out to. You need to first define your rule structure. In this case, our rule structure is pretty simple. If we actually look at our rules, um, it looks at what we would consider to be something like a pattern, okay, which is kind of your if part. If this is matching to something of this kind of format, and then you have a then issue here, all right, in which case you may have one of a list of responses that you may end up wanting to um, provide to the user. And as you can see here on line 81, that REST will essentially construct this list by looking at the rest of the actual um, uh, the rest of the actual list and then maintaining it as a list structure rather than actually creating a list of con cells. Um, So one way of actually attacking this is, and let me just go ahead and split my screen for this and bring up um, our kind of little project, is doing what creating what's called a rule-based translation tool. And I'm just going to kind of show you something that cover this piece of code that I saw inside of the book, particularly. I think actually he wrote this in, if I'm not mistaken, this is already in Og's functions. If I just pull this rule-based translation, no, hold on, where was this? He created it. I know it's in his and I'm just doing a quick search just to make sure that I get the right right file that has this. Translator based translator. Pat match. Okay. Lisp pat match. This guy. All right. Yes. Go ahead. Rule-based translator. Okay. So let's take a look at this. One way of generalizing this structure, and let me put the diff here as to what this looks like here. We could see that we could generalize two things. The rule structure that was provided, the um, the list of rules. So you want to provide some sort of database of the rules that's in of this structure, okay? Um, and you want to provide some sort of matcher, okay? That could be a function of some sort to this, and you could define also then the what they call the action, which is if it's true, what should you do, and then the rule then is if else, right? So then it will then call essentially the rule then rule on the database. Okay, so basically it will get the rest of the rules and then recall the function here. So what we could do is we could generalize this to essentially this kind of function, basically where the first input is our actual input that we're trying to match against our database of rules. Then we could then check and see if it, we have our matcher, our rule if, our rule then in action. Um, the matcher will check the rule if they match, then it will go and run the action sublist. Okay, as you can see here, the sublist is actually what we leverage. And if not, we then recall essentially the function to go and apply the action to the rest of the rules. All right. So what's nice about this structure is it's pretty useful, right? So what it does is it checks to see if our rule if our the first part of the database matches, right? Just like what we did here. Think about the pattern match on the left hand side. Okay, and the rest of the structure is basically the same. If it's not failed, then that means we've actually encountered a list. So we need to take the responses, which is the rest of the rule, and then we apply sublists on top of those rules. So we end up calling the rest of the rule sublist on top of uh, the result, and we can then move on. So how do we take this? Because there's still one thing missing here, which is the switch viewpoint. How do we actually switch this to leveraging um, the rule-based translator? Well, one way of doing this is basically um, you're going to end up creating in the action. We basically take these two sublist viewpoints and we actually provide a substitution. Okay, so we essentially override the action key argument with a lambda that essentially implements this. So let's see how that kind of looks. Um, and I'm just going to go ahead and write it underneath here just so that you can see this. So Eliza roles input, right? And then we're just going to call the rule-based translator, and on the input Eliza rules, and our action, because we're not going to actually override the matcher and the rule if and rule then, because that's going to be the same. It's going to be a 2-argument lambda function. If I can actually put a parentheses here. Bindings, responses, and what this does is it calls sublists, okay, and PAIP switch viewpoint. Oops, if I just can type in correctly, viewpoint. One second, for some reason it's not recognizing that I have this loaded in as part of the. Oops. 1 second, did I do? Trying to make sure that everything is appropriately loaded because I should be getting uh, Okay. I'm gonna have to restart my REPL because it looked like where the location of where my clone of the PAIP project wasn't actually available when I reloaded this, and it didn't catch it until later on. Give me a second. Okay, and let me do this. This should also catch it. Okay, good. All right. So now that's good. All right, and let's add. Right. So we just do switch viewpoint bindings on our responses because we're doing a random element. We're going to do random element on our responses. And we need to also put this like that. Okay. So if we actually load PAIP requires ELIZA 1, this is going to notice that we actually undefined functions. Okay, 1 second. I forgot to add this, and we need to add pattern matching into this guy here. So let me just go ahead and do that. Now, I'm not going. This is just clearly me. I'm making adjustments for the sake of simplicity, but this isn't something that we need to actually go and submit because this is just for us to see the kind of changes that you'd want to make. Let's see if this would load. It did not. Let's go ahead and load this guy up. Okay, for redefinitions, non-style warnings. And let's go and reload this. And just for the sake of simplicity, what I'm going to do is where is it? Rule based. There we go. I'm going to go ahead and comment this guy out just so that, I mean, we shouldn't have to do this because we defined it later on, but I'm to be kind of forcing the recompile should have worked. Okay. Let's see. If we call now PAIP ELIZA 1, is there an ELIZA here? Yeah, this is fine. And we just do a hello. Oops. Hello. Oh, right. Because I have to, this is the, you can see that this would, oh, sorry, I have to rerun the interpreter when I run that. There we go. If I do hello, you can see that it's now using the rule-based. You may not see it now, but it is using the rule-based translator. Is what we could certainly. I can actually show you here. Just so that you could see that this is running. Running rules. Okay. Okay. I'm gonna have to rerun here. Where's the required function? Yeah, this guy. Pat match. And let us run ELIZA, hello. Why is that not working? There is a particular thing that I missed here. 1 second. Switch viewpoints. Oh, let me do something here. I don't need to do that. Okay. I could do this. Running rule-based version. Okay, and let's do that to go and do this, and just to make sure. Okay, so it's actually not running the rule-based version right now. How do I fix this? One way of doing that is obviously we could reload the project, but that's going to require me to restart my Lisp. One of the things that you'll end up recognizing when you're playing with different when you're doing what I'm essentially leveraging, which is using a lot of uninterned symbols, is you will hit this conflict of redefinitions that end up happening quite a bit. And the only reason fix is either exporting the symbol or restarting your Lisp so that you can get the updated changes. It's not a real fun thing to do, but if you don't know what your API is when you are working through some of these things, this is something that I've noticed that you end up having to do while you are trying to finalize what's part of your public API. But that does not mean that you should go in and willy-nilly, what's the word? Uh, Export symbols, because sometimes you will forget that you don't want to export a particular symbol, and yet it's part of your public API. And now when you release your library, you're kind of stuck with it because other people will notice that it's there. Okay. Let's go ahead and do this. And let's do PAIP, Eliza. Oh, so I'm going to have to do requires Eliza 1. And then if I do this, and I do this, you'll see that. So it's still running through it and still searching through it, but it couldn't find essentially a hello version of this, which is surprising, but I'm not completely surprised. Right. So do is hello. Let's see. State your problem. Oh, right. I keep forgetting this. I have to run this in so one of the things I keep forgetting is I have to go and run anytime we make changes, because not all the symbols are interned like I mentioned earlier. I can't actually run any of these programs without actually being in the PAIP namespace. And now you can actually see that this is actually working the way we expect it to. So for the remainder of this discussion, I'm just going to go ahead and maintain myself in this namespace. Um, Again, for folks who haven't done this before, in Doom, which is actually a front end to Sylvester or Slime, Slime and Sylvester has the same key bindings when you're trying to switch between packages, which is the comma operator, and then you could use set package command. Or if you're in Slime, you could also do, I believe, command P is, what's it? The bang P is also a shorthand for set package, and you can use that to actually go and change your command. But once you do that, it'll list you all the packages that are available in your image, and then you just pick PAIP to switch to it. Now, the reason why MRS, if you're coming from, if you're in Do Emacs, space MRS, which normally switches to the package, um, didn't work, it's because in this file we are not actually in any particular package. Okay, so that's the reason why that didn't work. All right. So now, um, let's talk about search. Um, Both technically ELIZA and GPS, although GPS is more in this state, we have been we looked at this as being a problem in searching through a set of solutions for a particular for a given state. Okay, um, you have, you know, in many ways this tree of different solutions giving in a particular given a particularly input state. Okay, a particular input state, you will have particularly a tree, maybe a multitude of solutions to that input state for any sort of problems in search, okay, generally speaking. In GPS, that state was a kind of set of rules, a situation that you provided. If you recall, we had to say if I had money and I need to take my kid to school and my car was broken, I would potentially just put him in a cab to send him to school. And then the goal state of student in school would end up being accomplished. A lot of these search problems, though, are still technically that's a quick path, right? But a lot of these search problems tend to be ones where there are multiple solutions that you want to go and go through. So search problems then become what's called non-deterministic because you don't necessarily know what is the best what you know what is the best path to the ultimate goal, right? And this is general for all AI problems, whether you're talking about, search as to finding a, a strategy, as in the case of GPS, a general problem solver, a plan to actually go and accomplish some goal. Or in the case of ELIZA, um, searching through a set of solutions or responses for making and giving an appropriate response. Although in this case, we don't necessarily talk about Eliza having that because its solution to that was very simple. It ended up just taking a list of responses, not trying to encode any sort of context, and then just provide a random response for any given question and or dialogue that you provide. So you can ask the same thing twice, you'll end up getting potentially different answers. Even though if you were doing this in kind of a real natural language or natural problem, uh, like natural language processing or natural language understanding sense in the realm of a lot of these newer generative AI solutions, it will try and figure out some way to extract some piece of the context in which you're actually asking a particular question and give you a more appropriate answer, which is a type of search that you would end up incorporating in your systems, right? Norvig talks about this. It has a set of like tools that you could end up building around this kind of notion, right? Mainly because of the fact that the data structures that are related to search often in, end up being the same, right? In a lot of these different problems in search, they almost always end up using the same data structures, more often than not, a tree and or a graph, all right? Although, for those of us who have taken data structures in school, we both know that technically a tree is a type of graph. It's an acyclic graph, right? So they're all graph search problems essentially that you'll end up encountering. And 6.4 kind of covered a lot of these tools. I ended up realizing when I was browsing through this just a few minutes ago, this chapter, that apparently A star is much later in this, so we might actually get to cover it today. I have to see. But I want to at least mention to you that there are a couple of algorithms, known algorithms, that are available to us. The reason why I bring up A star a lot is because in search, especially for those of you who may have done any sort of game programming, a lot of times when they're doing path planning in games, they end up almost always implementing A star just because it's simple to implement. And we'll see how to implement this from scratch inside um, our discussion of uh, search. But to begin with, I think it's important to kind of talk about what is a search problem, right? I think it's important for those of us who haven't ever encountered search problems formally to kind of get this sense of what is a search problem, right? Norvig defines it as essentially what something that has four features, right? Um, I wouldn't necessarily put it that way, but technically it is a very formal way of defining it. So basically, for any search, you have um, uh, your start state. That is essentially what is known. Okay, your environment, particularly stuff that's related to what the agent needs to observe, because those things that it needs to observe has a direct effect on how it needs to take actions in order to accomplish the next thing, which is the goal, right? The goal state. And you may end up having in some situation a set of goal states. Okay, so this may end up being multiple goal states, uh, and then in which case, obviously, it becomes kind of a situation of compromise. After this, you have essentially the strategy that you have, okay, to determine how to actually go about the search. Okay, and that strategy takes you to and this is a function essentially, okay, uh, order in which search occurs, okay, and then your strategy ultimately takes in your state, which is not necessarily the start state, but in the beginning it's the start state. um, Most often it's going to be the current state, and it returns you potentially a successor or list of successors, okay, that can be reached from that particular state. In the realistic situation, right, it will, well, the idealistic situation, you end up having a single state in that's going to be returned by the strategy function, which is your search function. But often in real situations, you're going to end up having these multiple successors, and then you have to determine which successor is the path that you'd want to go in first. And then you can, in some search strategies, allow what's called backtracking, where you end up recognizing that this path is a dead end. You go back to where you had multiple successors, and then you go down the next path. Okay, so that's exact kind of a 10,000-foot overview on how search kind of works. Um, the search strategy for each different search problem is different, obviously, right? In the case of, say, GPS, if you recall, they use something called that we talked about means ends analysis to actually go determine how to um, move forward in the search, and that was particularly determined by the operators that were defined, that was defining the uh, the rules database that we use to ultimately solve the particular general problem solver problems that we were encountering with. In the case of other things, it could be a different type of weighting that's on top of the graph, where you end up using an ordering function to determine what state you need to actually go look at next. Okay, so when you're looking at these problems and you're looking at search strategies, you end up often hitting um, uh, this sort of formalization of a search problem. And you'll even notice when people talk about the total number of states in it, they'll say, "Oh, well, this is the state space," which is all possible states inside of the graph. They're not talking about how they're interconnected together. They're just saying these are all the possible states for this given particular problem. Okay, you can construct a state-based graph to include what they call successor relations. All right, those are edges in your state space graph that would essentially tell you from this state I can go to these other states. And naturally, in the case of trees, um, you'll end up noticing that in some state spaces you won't have cycles, which makes the search somewhat easier in the case in that you don't have to worry about visited states a lot, um, unless you're doing backtracking. And if you're backtracking, then backtracking search strategies have different ways of knowing what direction you would have to go to and what you have to keep track of what states you have visited and what states are remaining to visit before you could say that you've exhausted the search and you haven't figured out a solution and or you may have returned a solution. All right. So we're going to kind of cover this in detail, but first we need to kind of determine, how do you end up wanting to write um, this these search strategies? Well, again, we can first start with tree searches just because with trees, since there aren't any cycles, there is a easy stopping state that you could just write out. In graphs, if you end up having to go through it, you have to also account for cyclic graphs, and so that way you don't accidentally go into an infinite loop and you have to keep track of visited nodes and all this kind of stuff. Um, so Norvig actually created a tool that we're going to leverage here called Tree Search, and it's available. And we're going to first go through it, and it's a different type. There are different types of way of implementing Tree Search. Um, but once we look at it, we can actually first talk about what it is that how he's leveraging con structure for implementing these kinds of tree searches, and we may even be able to write our own based on what we see here. Um, while we're going through this, I want to remind the audience that these tend to be open discussions. So if there are questions both on the material and or just in general about Common Lisp, feel free to throw it in the chat, and I will answer them accordingly as I see them. All right. So let's first pull up the tree search question, which is in Lisp tree search. Search. There we go. All right. So one way of defining a tree search is you need to first provide a predicate for what determines a set to be a goal. Okay. Um, and in any search problems, the state that it provides or the states that you provide is the initial set of states that are going to be passed into a given function. Okay, these are your valid starting states. Um, The predicate for the goal state is more of a search through a set of goal states to determine whether or not, or a set of successors to determine if one of them is the goal state that we can go and encounter. But I'm jumping ahead. Uh, in this function particularly, Norvig defines search as essentially a set of valid starting states with a predicate to decide if we're in a goal state. You can see in the third argument, for any given states, the set of valid starting states is different than the successors from a given state. Okay, and the last argument is talking about the order in which we're going to perform the search. So if you look at this particular piece of code, okay, what it does is it checks to see if we have no starting states. If we have no starting states, then obviously the search is a failure to begin with, right? Otherwise, what we do is we call our goal predicate on the first of the given set of states. So did we reach in a given state? Okay, so the list of starting states, the very first, we're going to go through the list to see if we need to go through the rest of the states. Um, we check to see if that first state is the goal state. If it is, then we're done. We just return it. Okay. Otherwise, what we end up having to do is we need to first call and then perform a tree search on the set of successors based on the order that is returned by the combiner. All right, the combiner, I didn't really like the name of this when I saw this. It's kind of order strategy, kind of what it is, but I'm not entirely sure what the choice is. But that's what the combiner is. The combiner is basically you get your successors, the rest of your starting valid, your the rest of your valid starting states, and you determine based on the combiner strategy how should you go about to um, perform the search. Okay, and what's important about this is the order in which the arguments are being passed into the combiner does not necessarily mean that that is the order in which those states are going to be searched on. Okay, and that's I cannot stress this enough. Like when I looked at this, I was like, okay, why can't you just simply, do um, this the rest first and then the successors because that's just set of your valid states. And then I thought about it and I was like, oh, well, technically, um, that would be kind of like a breadth first search because you're essentially using you're exhausting all your starting states and then you're exhausting all the relevant successors and so forth, which doesn't really make much sense when you're trying to create a very intelligent search strategy. Um, but that's kind of the effect of tree search, and that is essentially any sort of tree search. Okay, so we can actually leverage this generic algorithm for tree search to actually implement different types of search strategies. The first one is naturally depth first search, as we can see Norvig actually implemented with this. And that actually was a lot simpler than you'd think. So you you create an initial start state, and this start state is just a single node. Okay, and then you pass your goal accordingly and your successors, and you can see that all our strategy for actually combining them is nothing more than we pen the list because we are going recursively until we hit kind of like a dead end, and then we go back and then hit the next we'll backtrack and then go and visit the next child in the tree that we've encountered, and we keep doing this until we hit a leaf that actually reaches the goal. So this makes understanding depth first search pretty damn simple. um, with 1 second. So how would we end up leveraging this? Um, well, there's this example that he wrote that I wanted to kind of go through just because this one looked pretty interesting based on the fact that he was computing the list um, uh, pretty using just a simple computation here, and that is the so in the book he had a binary tree that he defined as an ordered binary tree where the root elements started with one, and then the successor elements of the children were essentially the left the subtree is basically starting with plus one and then plus two and then so forth. The each level kind of uh, changed through the ultimate successors. So it ended up creating kind of a list of like say 15 elements for the first tree, and then he leveraged this to actually go in and implement say um, uh, the binary tree function. And the way he did it is he created essentially these two functions. This is actually constructing the binary tree. This is our goal, and then he encountered how to what's it he leverages this to actually compute on the fly the actual tree. Okay, so I want to kind of see how this kind of executed because this was pretty neat because then you could do on demand like calculations. So the first thing we need to do is we need to say that we want to leverage debug search. This is using the PAIP tools for those of you who are on the stream who haven't seen this before. We've introduced a debug functionality when we were talking about GPS. And now we're just going to go and call depth first search on this particular function by just doing depth first search here. Sorry, depth. There we go. Our initial value is 1. Um, our goal is 12, for example, and we're going to go ahead and use binary tree as our combiner to compute the next list. All right. When we run this, oops, 1 second, I'm gonna have to do PIP requires search. Go. Let's try this again. Uh-huh. 1 second. We hit a problem in the calculation. Um, mm, let's do. Let's change this just for a second. Okay, so this worked. So the simple case seems to work the way we're kind of expecting, but for some reason this could not encounter 12 very quickly, depth first search wise, which is surprising. Um, let's try another load, another like implementation that is. Um, let's try 4. Okay, so it's able to figure that one out. But that is a degenerate case because of the fact that the way it is implemented, it'll keep computing before it actually went back. Let's try one other implementation here. Let's go to oh, right. So the reason why the previous one didn't work is because since we are doing depth first search, we're always prepending, right? In the binary tree, we're computing the next list, right? So it will never actually go into the situation um, is because it keeps going into the left-handed branch and we're never actually giving it an end. It's and we're computing on the fly again here, as you can see here. It's always going to do the degenerate case. So in these, as long as the value is on the leftmost node of the tree, it's going to actually end up encountering it. So if we want to just break this here and just simply do 5, we'll automatically hit the degenerate case because it's going to keep going. And that's because we keep growing the size of the number of nodes in leftmost, and we decided just to use the leftmost node to actually go and check to see if we're hitting the goal. We're never actually encountering the rest of the tree. So it's basically a never-ending leftmost node search that we're hitting. So we're hitting kind of the degenerate case. Um, Another strategy of trying this is obviously instead of using depth first search is breadth first search. Most of you may have encountered breadth first search in your schools. It's probably the easiest thing to do. Is kind of a level order traversal. You start with the goal. You hit what's called the horizon. The horizon is all the immediate successors. Okay. In the case of constructing this inside of Common Lisp, you just need to prepend the list and then it'll just do kind of like first level, second level, and it'll keep on going through the horizon until we hit this. So how do we actually end up leveraging breadth first search, as we can see here? Breadth first search, the only difference is uh, instead of append like we used in depth first search, we prepend. Um, so if you ever seen prepend here, if we describe prepend, you can see that this is a compiled function that takes in 2 arguments and just prepends uh, something to the start of x. So prepending in the case of a simple 2 to list 1, you'll see that it'll end up creating um, y is going to be the start of x. So if we ended up doing this the other way, if we do prepend 1, 2, you can see that, oh, sorry, my apologies. We end up hitting we're prepending essentially y to being the x. So what we have to do is sorry, what I meant to do is this. Now, you can see that this actually prepends these two lists together. So we took the second list y, which contains 2, and we passed it in it to 1. Um, so if you did the other one that I showed you, if we just took list 2, list 1, we end up having 1, 2, right? No big deal on that. But this becomes important when we're doing these kinds of basic searches, because if you have these, especially on the fly computation based searches, and you're using something like depth first search, you end up hitting this infinite loop. Whereas with the case of uh, breadth first search, it's actually pretty simple if we just simply change it. So if we do 1 is 12, and if we do prepend instead of, sorry, successors is going to be binary tree as our combiner. you can see that very quickly. We computed the actual calculation of the tree. So we started with 1, we computed 2, 3, then we kept going each of the layers, 4, 5, 6, and it wasn't until we kind of went through 12 iterations until we hit the 12th node naturally, and we actually go and return saying, hey, we found the node, right? So breadth first search, I think most people understand. Depth first search, most people understand because of how often we end up leveraging these two in our daily work. Um, the next one that I think is pretty interesting is, um, well, the one thing that's pretty interesting is if we define uh let's say a tree that is finite, then some of these things will become important. Like in the case of depth first search, um, if it happens, what's it? Depth first search will actually be faster than necessarily than breadth first search if the tree is finite, mainly because of the fact that you are going to hit kind of a logarithmic search pretty quickly, versus in breadth first search, um, we do it more or less in linear kind of order because it's, and additionally, with breadth first search, given the size of trees for certain trees and certain sizes of n, as most of you know, breadth first search will take more storage than depth first search because we only need to keep a half the tree when we're doing a depth first search. And this is depth first search without necessarily doing, this is including some form of backtracking because we have to backtrack to the previous generation to keep moving until we hit all the leaf nodes for a given subtree. So um, in this detail, we actually have a function called finite binary tree that Norvig created that would allow us to kind of generate some of these trees. So let's kind of see what the difference is when we use this finite binary tree when we run depth first search versus breadth first search on our computation that we saw earlier there. Um, so let's do depth first search. 1 is 12. And let's say we use finite binary tree 2048 to create our search. You can see that in this case, with depth first search, we were able to do it in a pretty short amount of time because of the number of search cycles we have to do it. Um, Let me try a smaller one just to even bring this home because I noticed that this is a lot more branches. Let's do instead of 15. You can see that in breadth first search we were able to grab our 12 in 3, 6, 9, 11 iterations, whereas if we did this with breadth first search, it's going to be a lot more. And again, this isn't kind of uh, a comparison, a search comparison between breadth first search and depth first search, because I'm sure most of you know already um, that in degenerate cases, both methods end up searching the entire state space. Um, but that's kind of in the worst case scenario. But the order in which they come and they search it is very different, and that's kind of important to realize as to when one is better than the other. Now, um, there are other types of searches that are out there, um, especially when you start using weighted graphs that we can implement using this tree search algorithms. The book kind of mentions a couple of them. I'm not going to cover all of them here just because I think it's important for us to kind of read some of this stuff and kind of discuss it. Two that I want to kind of call out and is one is what's it? Um, a couple of algorithms related to what he calls search guiding. So you're able to essentially tell through the use of a the weights usually in weighted like either some function that kind of says okay this is how much it costs to go down this particular branch. You can actually use that to kind of drive the search strategy to go in a particular direction. And um, two particular searches that can be used in this. I'm going to be kind of talking about uh, best first search, which is something that essentially leverages this kind of cost function. But then there's also this other one that I didn't even know existed called beam search that essentially allows you to use the cost function slightly differently. We'll begin with best first search just because best first search is just a pretty typical um, uh, ordering function. It looks kind of like anybody who's touched shortest path strategies like uh, um, Dijkstra's. It looks very similar to like Dijkstra's, um, whereas it orders the search nodes based on an ascending order of the cost function that you pass in. So let's see how that kind of looks like. There's a couple of helper functions first that I want to kind of touch base on. One is diff, which is basically doing the absolute difference here. Now, you want it, and the reason I want to bring this up is a lot of times when you're writing these AI algorithms, you'll create these small functions, these one-offs, essentially in this case, that wants to take the absolute value um, of a particular, well, the difference, the absolute difference between a number and some input. And what's important about that is from a program perspective and a maintenance perspective, and this is not just particular to Common Lisp, but this is good software engineering in general. When it turns out that your callback or in this case anonymous function can be attached to a semantic meaning, like essentially can be labeled to being a named function, or in this case we are returning the lambda because we're going to use a fun call later on because it's being part of the high order function that's going to be ending up leveraging it. If that helps essentially explain the algorithm, you want to actually go and label it accordingly, even if it means you're constructing this for different things. And what's nice about this is this is effectively a factory, right? For those of you who are coming from other more object-oriented languages, because you're essentially providing a number as an input to diff, and then it creates essentially a factory function that, well, a lambda for you that will return the absolute, well, the absolute difference between that number and some x that's passed into diff, right? Well, into the lambda that's returned by diff. So if we look at this, we end up, just creating 5 here. We end up getting some lambda function here. And then you can end up leveraging this by calling funcall on top of it. And you could see that it will always return this. And you know that if you do an EQ of diff5 and diff3, you could see that they're going to be different. And this is even the same for two instances of the same function because they are technically two different function objects in memory. Things to be aware of, just because this is kind of just standard, um, kind of common Lisp best practice. Uh, so just like we saw diff creating another function factory, so we have another function factory called sorter. And sorter basically does the ordering that I was talking about. In this case, we are passing in um, some cost function, and that cost function ends up being the key to determine how do we order a set of states in ascending order, not in descending order, as you could see by that third argument to sort, which is, well, sorry, the second argument to sort, which is the less than operator. It's not less than or equal to, so it's not, it's a strict inequality, not a it's not a it's not a closed interval, it's an open interval essentially, within a particular range. And leveraging these two functions, we could then implement best first search by essentially instantiating a sorter function that takes in a cost function, and then use that to determine how do we order a particular set of goal states, to see if we can reach a particular goal. Let's see how this looks when we are trying out a couple of things here. Are there any questions about this so far? I know a lot of this is just basically code review, but this is the reason why I'm calling this out, is because later on when we start talking about the um, algebraic solving and then maxima, some of the stuff will the searches stuff will become somewhat useful. Um, so uh, so best first search. Let's try this example here. So okay, so here our successors is going to be binary tree, but our cost function is going to be something of diff 12. So let's see what happens when we do this. So you can see, compared to breadth first search and depth first search, even best first search is much faster. So the fact that we even attached a cost function alone also shortened the search somewhat, okay, in this space, right? Which is very, very um, useful, right? Um, and so as you leverage this kind of stuff, and as you're playing around with this stuff, you will see immediately that the these cost functions become very, very helpful in determining um, how to drive a particular search, and you can write more appropriate cost functions. Now it's no longer how do we go and associate the space, is based on what we know in the environment, can we actually weight it in such a way that a particular search strategy is favored over another search strategy. Okay, so there's another example leveraging, say, a different type of cost function here that I'm not going to go to, but you can see just by playing around with these different callbacks, well, these different cost functions that you construct, you could drive the search in different directions. So I encourage you to experiment with some of this stuff in what was provided. Uh, the other one that I kind of wanted to touch base on here is beam search, because this is, like I said, something I've never actually encountered in my previous AI classes that I've taken in school. Um, so the way it's defined is well, is based on a different a premise, which is all the current searching methods that were discussed so far were essentially increasing lists of states. Um, but for cases where you have a large number of potential solutions, and you're effectively um, trying to find a needle in a haystack, as what Norvig uses as the analogy, you're going to end up just sitting around sifting through a lot of invalid solutions, right? Um, so there has to be a way of being able to discard unpromising paths, essentially. Um, uh, s- just because it will help at least um, save enough space given how many solutions you have to look at. Although at the same time, it may risk of giving you a situation where you can't find something in the solution space because you had to go through an unpromising path to get there. But um, being able to run it multiple times or the same search once you have it, this kind of pruning approach is very worthwhile. And beam search gives you that. It's a best first search that looks at only a fixed number of alternative states. Uh, and the reason why they named it beam search because they use the analogy of shining a light through the darkness of the state space to kind of name it, which is kind of funny, but interesting. Um, so let's take a look at beam search. Okay. Um, I'm gonna pull this up here, and as we go through it, um, so what beam search does is it's a variant of what we saw earlier with best search, best first search, but um, it adds a level of depth, which gives you the kind of somewhat of the benefit of a DFS, but also with best first cost functions being part of driving it. Okay, so you don't know. So effectively, it's a DFS that doesn't backtrack indefinitely. It doesn't actually go through and searches all the space because it's leveraging the cost function and what he calls the beam width to actually determine what your searches are going to be. All right. So here we see now an extension of best first. So the addition to beam search is that beam width there that you see in the last option. The previous four options to the arguments are basically just stuff that we've already talked about um, with best first search. But the important thing to look at is that lambda function there that takes in the old solution and the new solution and then runs the sorter on with the cost function on top of the old and new to determine which strategy or which successor state should we go on next. And basically, it leverages this beam width to determine if the set of solutions that were provided by old and new, if that is bigger than a particular beam width, um, then it creates essentially a subsequence of those sorted solutions and cuts off the rest. It truncates it to essentially to be only the beam width. So you're always only looking at a certain number of solutions and that's it, right? So how we would use this is let's leverage the Price is Right kind of differentiator for this, which measures the difference from price for a given penalty. And so we're going to use this beam search to actually run a search on top of um, the same like numeric binary tree that we've been looking at. So beam search 1 is 12 is what we're looking for. We're going to create in our successors using a binary tree. Again, to compute this, our cost function is going to be essentially Price is Right of 12 to see the absolute difference in price. And our beam width is only width of 2. And you could see very quickly that this search has made it even faster by just simply adding that beam width because we're now pruning out results and we're just, moving things up. So now you're able to get through your search space within only 5 iterations. And notice we haven't actually changed binary tree. We haven't actually changed how we're computing the rest of the search space. The only thing we've added really fundamentally is a set of factors that we're using to guide the search, which makes, this is kind of like pretty cool. So those of you who have never actually encountered this kind of like experimentation, this kind of search, you might be thinking, oh, this can be leveraged in a lot of solutions. Yes, for a lot of different types of problems, the search of strategy could determine the speed at which you can get to a particular solution and the number of times you could try a particular solution. And a lot of this is really trial and error, um, to determine which one would be appropriate. Now, I'm going to kind of open the floor to questions because honestly, I didn't have the time to actually go and um, look at the other search strategies. Uh, Mainly because I was playing around with Beam Search just to see what the hell it does and tried to understand what it was doing. But but if there aren't any questions, um, well, I'll just open the floor to questions and comments and see if there are any questions or comments on this. Okay then. Um, Looks like there aren't any coming in from this. Doesn't look like we have any coming in from the Jitsi. All right. If there aren't any questions, I'm going to go ahead and say that's the end of our episode for today. Tune in next week where hopefully we will be able to finish up the rest of Chapter 6. Um, and we'll look at more interesting search paths inside Chapter 6 for tools. And that includes my favorite searches, which is graph searches, and that will include, or as what I mentioned earlier, which is a star search, is actually in this book. We're going to try some other stuff related to this too as well. And at the end of this, we're going to actually try and implement GPS with has a proper search problem next week, and then try some of the exercises. Um, so I hope to see you guys next week. Thanks for joining. Enjoy your Saturday. And those of you who are watching this on YouTube later on after the recording, if you like my content of AFP, please do like and subscribe on the channel and hit the bell icon to get updates whenever we hit a new live stream. As usual, AFP is available for people to give talks, both in Common Lisp as part of our weekly Common Lisp study group and general functional programming. If you guys have a particular talk topic that you're interested in presenting, please reach out to me. I am available on functional programming Slack, Tech 404, and I squat in the uh, Lisp Discord server, has Bugram. All three actually. When you're if you're on Tech 404, Functional Programming Slack, or Lisp Discord server, I am Bugram on all three. Um, just ping me, DM me, give me your talk topic, and I will schedule it accordingly. Um, Hope you guys enjoy your Friday. Thank you for joining us. Bye.